Hello, guys. So this is a physics problem, and this is one that deals with vectors in the conventional ij k hat notation. It's about a car that moves along a horizontal road with constant velocity. Vector initial velocity vector is represented as some initial velocity parameter in the I hat direction, which is 37.6 meters per second in the I hat direction, until it encounters a smooth incline hill. It climbs the hill with the constant velocity b1, which equals b1 I hat plus b1 j hat. This means that as it climbs the hill, it does it with the same magnitude along the horizontal axis and the vertical axis. And the period of time during which the car changes its velocity is delta t equals 1.88 seconds. Notice how the units are already in international system units. Part A says enter an expression in Cartesian unit vector notation. That means ijk for the average acceleration of the car during the given time period using the symbols. And then part B says what is the magnitude in meters per second squared of the car's average acceleration during the given time period. So first with symbols, then plugging numbers. For average acceleration in vector notation, that is the change in velocity in vector notation divided by the period of time in which that change in velocity changes. When you're doing algebra with vectors, subtraction and addition works the same, almost the same way as regular algebra, except that I components add or subtract from each other, and j components add or subtract from each other. You cannot combine j's with i's, and vice versa. The division by delta t, which is the period of time, you can write it that way, but you could also write it as a 1 over delta t up front, the calculations of the vectors as a scalar. Now, as for what I mentioned about the operations between components, the change in final velocity minus initial velocity results in final velocity x for the I hat minus initial velocity in x for the I hat, plus the change in velocity in the j hat direction, right, over delta t. Turns out we can collect terms to make a single coefficient up front each one of the unit vectors, and then we have for each one of the expressions change velocity in x over delta t I hat plus change velocity in y over delta t j hat. Now we plug in the actual values that are given, the symbols, not the actual numerical values, but the symbols, right? We know that both final velocities in x and y are v1, so I go ahead and plug in those. I also know that my initial velocity in the x direction is b naught, so I replace b naught x for v naught. And I also know that my final velocity, my initial velocity on the y is 0 because I only have initially my velocity going in the I hat direction. So therefore, the answer is v1 minus v naught over delta t I hat plus v1 over delta t j hat. That's the answer A. Now, how am I going to encounter what the average acceleration is by plugging in numbers? Well, first of all, I have to find out what that v1 is, because I do know what v naught is, but I don't know what v1 is. So I use the argument of conservation of energy. That means that if there's a smooth incline and no friction, then write the moment as it increases that incline, assuming the potential energy, gravitational potential energy is almost zero, then kinetic energy final equals kinetic energy initial. And so I equate the equations and I get to the conclusion that B final must be equal to B initial. And we're talking about speeds here, not velocities. Now I find the magnitude of the speed, and that gives me square root 2 B1. But that final speed, because of conservation of energy, should be also equal to the initial velocity, which is V naught. So then I found the conclusion that V1 equals 1 over square root 2 of the initial velocity. Now I go ahead and plug in those values for the average velocity as a vector, and I end up doing the algebra and then factoring out whatever I can in scalar, and that ends up as V naught over square root 2 delta t, parentheses 1 minus square root 2 I hat plus j hat. I continue plugging in the numbers, finishing up with the calculations, and I get a negative component in the I hat direction and a positive component in the j hat direction. That is the average acceleration. And to find the magnitude, what I do is I square both components and take the square root of that and multiply by the scalar outside, which turns out to be 15.5 meters per second squared. Thank you so much for listening.